Dashini, and the question that has been given to me is presentation 2, Group C, question 5. Let characteristic k n is equal to 1 and f of x is equal to x power n minus 1 belongs to k. Show that the Galois group GF of f of x over k is isomorphic to a subgroup of un, where un is the group of units in set nz. Now, before we get to the proof of this problem, we'll have to recall a few definitions first. Nth root of unity. A root of polynomial x power n minus 1 for a positive integer n is an nth root of unity in a field. A root of unity is nth root of unity for some n. Now, since it is the root of the polynomial xn minus 1, we can clearly see that there are at most n different nth roots of unity in a field. Now in C, if we put theta is equal to 2 pi by n, then xn minus 1 has the n roots e power ik theta, where k goes from 0 to n minus 1. These appear in the complex plane as the vertices of a regular n-gon inscribed in the unit circle. They are at equal distances from each other in the unit circle. Now, let the base field have characteristic P. If P divides n, then the x power n minus 1 is equal to n x n minus 1 is equal to 0. We see the derivative. So, x power n minus 1 is not separable. Conversely, if P does not divide n, then x power n minus 1 and nxn minus 1 clearly have no roots in common. So, in this case, x power n minus 1 is separable. From here, we arrive at the observation that if characteristic f is 0 or n characteristic f is 1, then x power n minus 1 is separable polynomial and has distinct roots in f bar. Now, let z is equal to alpha 1 to alpha n, and it be the set of all distinct roots of x power n minus 1 in f bar. Then we can say that z is a cyclic group of order n. Why do we say so? Let k be an extension of f. The roots of x power n minus 1 in k are distinct, and it is clear that they form a subgroup of k under multiplication. So from this we can see that z is a cyclic group of order n. Now let's look at some notations which we'll use further in the question 2. Mu n is the set of all distinct nth roots of unity, and let tau n be a generator of mu n. When xn minus 1 is separable over f, we see that k mu n by k, this is Galois. Why do we say so? See, characteristic fn is 1, gf makes sense too, because characteristic fn is 1 and polynomial is a separable polynomial. So the splitting field will be the normal extension. And so we can say that field generated by all roots of x power n minus 1 over f is Galois. Because here, now we will see about cyclotomic extensions. We will define cyclotomic field of order n. A splitting field of xn minus 1 over f is called a cyclotomic field of order n over f. This is true also that cyclotomic field is Galois extension over f. If characteristic f is 0 or characteristic fn is 1. Now we arrive at a proposition, and this proposition is what I have to prove from my question 2. Let characteristic fn is equal to 1 and f of x is xn minus 1 belongs to f. Then the Galois group GF of the polynomial f of x is isomorphic to a subgroup of un. Let's see the proof. Characteristic of fn is equal to 1. This would imply that f of x is separable. We saw that when we were recalling the definitions. and also this would imply that it has n distinct roots. Let Z alpha 1 to alpha n be the set of roots of f of x in f bar, and E is equal to f of alpha 1 to alpha n. For alpha I, alpha j belongs to Z, they are the roots, so alpha I, alpha j inverse will also be the root, so this power n minus 1 is equal to 0. This would imply that Z is a subgroup, and which would imply that Z is cyclic because it is a finite subgroup. Now we would define or construct a map phi such that phi goes from GF to automorphism of Z, where Z is the same, it's the collection of roots from alpha 1 to alpha n. Now we will see that we'll take sigma and then this map here sigma, and then we'll restrict sigma to Z, we'll map it. So now we can take any automorphism of E, okay, and when we see it restricted or see it over Z, we see that any root of the polynomial f of x, let it be alpha I or alpha j, it takes it to another root of the polynomial f of x. So we see that the image of Z under sigma is again a Z, and so we will get sigma restricted on Z as an element of automorphism of Z. So the map we are talking about is well defined. Now we say that phi is an injective group homomorphism. Why will so we will see. Take sigma an identity map. E is generated by E is equal to alpha 1 to alpha n. Sigma is an identity on F. So therefore sigma has to wait. This here is F of So sigma is an identity on F. So therefore sigma would be an identity on E2. Sigma we have taken it as an identity map. So we see that the kernel is trivial, and therefore we get that the map is injective. Now Z is a cyclic group, so automorphism of Z is isomorphic to M bar, where Mn is equal to 1 and this would be equal to Un. So we can say that here when we saw the map from GF to automorphism of Z. So since here automorphism of Z is isomorphic to Un and the map is 1 1, so this would imply that GF is isomorphic to a subgroup of Un, which is what we have to prove in the question.